Hello, my name is Brian Corbett. I'm in charge of the Monolithic and Heterogeneous Integration theme within IPIC. So I want to tell you a little bit about IPIC, which you may already have come familiar with. But essentially, we have 4 different themes encompassing maybe 120 different people. These themes look at packaging and hybrid integration and monolithic and heterogeneous integration. These are technologies which are used then to apply to different applications. The 2 application areas of strength within IPIC are the optical communications theme and the biomedical theme. So the whole idea is that we will make devices in this monolithic theme. We will package those devices and then we'll apply them in these applications. So I'd like to talk to you a little bit about the photonics industry. Unlike electronics, it's much more diverse and coming at different, angles. Perhaps the most common one is the display that you're looking at right at this point in time. It's on a computer probably, and it's backlit by some LED or some fluorescent tube. But of course, before that, we had the cathode ray tube, which lasted for nearly 50 years in terms of its longevity. But after that, there was a huge change. First of all, with plasma displays, then liquid crystal displays, and then moved on to OLEDs, quantum dot displays. And now the most recent innovations have been in these micro LED displays. So that's where we're using semiconductors to generate the colors. So this is really going to revolutionize displays again, particularly when it comes to large screen displays. Another huge area for semiconductors and for photonics in semiconductors is solar. It uses the same material as is used in electronics, namely silicon. And at this stage, solar energy is the cheapest form of new electricity. There's not much of solar energy in Ireland, and that's not because we don't have enough light. It's just that we haven't embraced that technology. But you can be sure that in the next few years, you will start to see fields of solar panels like this. Another huge area and huge development that's taken place in the last few years is particularly associated with the mobile phones is a camera. So you now know that you've got megapixel 10, 15 megapixel cameras on your mobile phone, and they can give you remarkably good images. Now, the area that we have most interest in and most longevity from our point of view has been in communications. In other words, the internet. And we've evolved the internet from initially, point-to-point links, maybe 50 megabits per second, now to multiple channels, all operating at 10 or even 40 gigabits per second. We can transmit the signals over 100 kilometers without the need for regeneration. And now we can multiplex many different wavelengths along the same optical fiber and really generate terabits of information along a single optical strand. So really remarkable developments over the last 20 to 30 years. I suppose there's a new change as well, and that is with the mobile phone. Now everybody's got access to bandwidth. So they're sending information back and forth all the time from their personal device. But of course, at the end of the day, the different devices have to communicate with each other, and there's not sufficient bandwidth in the radio frequency spectrum. So what you have to do is to send the signals over optical fibers. And as I mentioned, there's an extraordinary capacity of light for sending signals over optical fibers. It's not limitless as some people originally thought, but actually, so that's a new area of challenge. How can you even send more information down an optical fiber? Another huge change in the last few years has been the emergence of data centers. Everybody's information now is not stored on their own personal device necessarily, but on the cloud. And the cloud means you have a big, what looks like a factory somewhere in the world, And it turns out that a lot of them are in Ireland. And this one here is the Facebook data centre in Clonee in County Meath. And within that data centre, you see racks and racks of or corridors of these racks of basically hard disk drives. But of course, to communicate from your device, from where we are right now, to one of these devices requires optics. Optics, first of all, to send the signal to the data center. And then within this data center, all the signals are now sent using light. And even within the computer racks themselves, they are connected by light. And eventually we imagine that the computer chips themselves will be connected using light. So really, it's becoming a vital part of our infrastructure. And of course, the issue is about energy that's needed to send all that light. So light, where does it come from? So you're obviously familiar with the sun. It's a hot body, 6,000 Kelvin, and it gives you a black body radiation, which results in the light having the peak intensity in the green part of the spectrum. There's also natural phenomena to generate light, such as bioluminescence from algae in the sea. We can create plasmas and generate light in that fashion. And then we had also another man-made black body radiator, which is the resistive element in the incandescent bulb. But again, there's been a huge change in the last few years, because now we can actually make semiconductors, and by making those semiconductors very carefully, we can organize that they can emit green, red, or blue light. And of course, the light that we're interested in for telecommunications is in the near infrared part of the spectrum. It's emitting in the region of 1.3 to 1.55 microns. So if we look at electromagnetic radiation, it covers the spectrum, as it's called. It goes all the way from gamma rays, X-rays, ultraviolet, infrared, all the way out into the radio waves. So the radio waves, which are used in your mobile phone, have a frequency of the order of 5 gigahertz, which means that the wavelength is about 30 centimeters. So pretty substantial wavelength. So that actually means that you're generally in the near field of the radio waves. And the other thing is 5 gigahertz. Well, if you want to send information, you use all that bandwidth, and you can send 5 gigabits per second. By being clever, you can get maybe up to 10 gigabits, but that's your ultimate limitation. So you can't send any higher frequencies per channel because of this frequency. So if you want to send more information, you need to increase the frequency. And that's exactly where we are with light. With visible light, its frequency is the order of 500 terahertz. And so therefore massively different in terms of gigahertz. So similarly for the infrared part of the spectrum, it's the order of 190 terahertz, where we're operating at 1.5 microns. Now 1.5 microns is chosen because it turns out that optical fiber has a minimum loss at that wavelength. So we work with the intensity, wavelength, polarization, and phase properties of light in order to send signals. So as I mentioned, there's a comparison between electronics and photonics for signaling. Electronics, it's moving of electrons, but it's still, the information is communicated using electromagnetic waves. And these waves, because of the long wavelength, they interfere with each other from adjacent channels. So that means you've got to use coaxial cables. That means that the channel cross-sectional area increases. So you can't pack as much information into the same cross-sectional area because of that, compared with photonics. And you have this skin effect where basically the current is transmitted on the surface of the copper, which is the conductor. And that means, and you may know that the bandwidth of the computer essentially has not increased in the last 15 years. We increased the speed of your computer by having multiple CPUs operating in parallel. For photonics, we have the benefit then of minimal interference. We can have beams crossing each other and they still don't interfere with each other. So that means we've got a very strong information pipe, which means the amount of information you can send down a particular area. You've also got this business of wavelength division multiplexing. So you send signals of different wavelengths on the same channel, and they don't interfere with each other, which means you've got independent channels when you separate them at the far end. Free space beaming, two-dimensional functionality, and of course the light essentially is quantum. So you detect one individual photon. So that has its own benefits as well. And that's because the energy of the photon is high, whereas in the electronics domain, the energy of the photon is very low, and thermal effects dominate in that point. So remarkably, it's more efficient to send signals by performing an electronic to optic to electronic arrangement than sending it in an all electronic way. So that's the basis of the internet and why light is used then for communications. So some circuits that you could imagine building with light are transmitters, things that are going to take in electrical signals and transform those into optical signals so that they can be sent over an optical fiber. Obviously, at the far end, you need to have a receiver that's going to take those optical signals and convert them back into electrical signals. But there are other elements that can be done, like phased arrays, which are very common in radio waves. Well, they can also be done with light. So you can beam light, for example, in distance sensing. So people believe also that neuromorphic computing, where you basically get a computer to work somehow like the brain, so that might have better implementations in photonics domain. And the fact that you can do two-dimensional beaming may suggest that you can somehow find a way to do smart calculation and therefore do artificial intelligence. Obviously, quantum computers are of great interest, and smart sensing are also being utilized to make circuits to detect certain gases in the environment or in your body. So let's just look at electronic circuits and how they've evolved over the years. The circuit is based upon the transistor, as you should know, and the first transistor was based upon germanium, discovered in 1947. It took nearly 10 years for the first integrated circuit, which basically had one transistor, one capacitor, and three resistors on germanium, and it looks pretty crude. Then CMOS technology, complementary metal oxide semiconductor technology, is a very efficient way of doing calculations, was invented in 1963, and by 2019, last year, we're now at what's called a 10 nanometer node, which is the smallest dimension that's on your transistor, and you can have 100 million transistors per square millimeter on a 300 millimeter diameter silicon wafer. So that's how far the technology has gone. If you look at the evolution in thousands of transistors per wafer, you can see the exponential increase that's still increasing. And if I look for photonics way down here, we're at 2015, and we're really talking about tens of devices per wafer. Okay, it started really to increase in the last few years, so this is the time. So we can expect a similar evolution somehow to that of transistors. Now, transistors are remarkable in terms of the technology. You have a transistor layer at the bottom of it is a cross-sectional view of a silicon wafer, and you have multiple levels of interconnect to get your signals out of your transistor layers. And so this, this is a very complex technology that has been mastered and it's produced in foundries around the world. So to use a circuit, or to make a circuit, you have to look at the elements. You're familiar with resistors, capacitors, inductors, and amplifiers that might be used in a PCB implementation of a circuit. So when it comes to silicon circuits, they're based upon transistors primarily. We've got resistors, capacitors, very few inductors because it's rather challenging to make an inductor, and connecting lines, these copper traces that connect one device to the next. As I mentioned, these are remarkably sophisticated with 100 million transistors, for example, on your circuit. So how on earth can a person design such a circuit and actually get it to work? And given that complexity, as I said, these are made in foundries. You yourself can go off and get a circuit made, and they're also made by the biggest companies such as Intel, Leakslip, and Analog Devices in Limerick. And the reason why we can make these circuits is that it's been broken down into building blocks, and there are design tools able to help you do the design, do the simulation, verify that your circuit will work, do a check that your layout for your circuit matches your schematic, has design rule checks, etc. So you can sit at your desk, know nothing about transistors themselves, know nothing about the technology that's needed to make the circuit, and yet you can make a very successful circuit by following your rules. So in the end, you have a layout, you have individual lines of metals and dopants and etc. It's got a circuit formula here, and then it's got a layout here. So all of these things can be done from your desk. This circuit will cost you between 10,000 and 100,000 euros for a circuit, 5mm by 5mm on a multi-project wafer run. If you want to make your own individual circuit that you want to do production on, it'll cost you multi-millions to get that circuit made. But the point is that you'll get multi-millions of circuits from that process, and therefore the cost per circuit is really in the cents regime. So of course it's got to work, because if it doesn't work, then you've wasted your multi-millions. So that's why this framework of software and that can allow you to do the design and the checking is absolutely vital. So as you can imagine, then the situation for photonics is far more primitive. It's like we go back to that original germanium circuit. However, we're very familiar with all the parts for photonics. Waveguides are the equivalent of the electrical wire. So they're going to transmit the light. But then we have all these multiplexers to join different wavelengths together, or split light, gratings, filters, and demultiplexers. Polarization, as I mentioned, is another factor. You've got to get your light from your circuit into your outside waveguide, which is an optical fiber. So you need some sort of coupling mechanism. You need what's the equivalent of your transistor, your power source. You need a laser. You might want to amplify your light somewhere. You need to detect your light. You need to convert your light into signals through modulators. You mess with the phase, and you have optical isolators. And also you need to have electronics to drive your circuit. So the elements needed for a photonic circuit are quite diverse. The other issue with photonics, and you'd say that's almost an advantage, is the fact is that photons are big when compared with electronics. So the effective dimension of a photon is its wavelength divided by 2 times its refractive index. And for 1500 nanometer light, so that's 1.5 microns in the infrared, then the effective wavelength is about 200 nanometers. So that's still a very small dimension. But when I mentioned that the size of electronic circuits goes down to about 10 nanometers. So this is 20 times bigger than that. So effectively the circuits are large, are going to have a bigger footprint than an electronic circuit as a result. So you can see that I mentioned there's 100 million transistors per square millimeter. In the square millimeter, you're hardly going to even get a laser into that dimension. So second thing is that the active parts, the things that are going to generate your light and modulate your light, they need crystalline materials, and these are very sensitive to defects. And these crystalline materials are very specialized 3,5 materials, indium phosphide and gallium arsenide. where the size of the wafers are limited. These passive waveguide devices then can be made in silicon, as you'll see in a moment. And we need to combine electrical functions and couple to the fiber. So here we are in 2020, and we're just about to enter the era of photonic integrated circuits. It's been promised for the last, I suppose, 20, 30 years, but actually nothing much has happened, as I said. But I think I really believe that's about to change now. And the ways you can do it are threefold, I would suppose, if I just look at it at a high level. The first is monolithic integration using this semiconductor called indium phosphide. It gives you really very sophisticated circuits, very high performing, but actually there's a problem. The wafers that you have of indium phosphide are of dimensions about 3 inches to 4 inches in diameter, compared with the 12-inch diameter silicon wafers. This material is very fragile. The process needed to make the circuit is very complex. And so I would say it's not mass manufacturable, although there are a few examples doing that. You may not be able to see the details here, but you can make very sophisticated circuits with multiplexers, with modulators, and all sorts of electronics, all co-integrated. The technology that's taking over now is this silicon on insulator. So what does that mean? It means you have a very thin layer of silicon on a layer of glass, which is on a layer of silicon. And this upper layer of silicon has got a thickness of the order of 200 nanometers to 400 nanometers, or maybe a micron. So it's extraordinarily thin. And this layer has got to be remarkably uniform over the entire 300 millimeter diameter wafer, which is possible because this type of silicon is used in electronics. The reason why this is used is because silicon has a high refractive index, and it can guide light very effectively over in a very tiny dimension. And because of all the advantages from the 50 years of investment in silicon technology, these waveguides can be made very smooth and therefore have very low loss for guiding light. Not as low as silicon waveguides, but still low enough to build your circuit. However, the problem here is there's no laser, natural laser on the silicon. You can also make circuits from silicon nitride, a dielectric material, which is also somewhat in between these other materials, and it's got good advantages as well. Here's an example of a silicon photonic circuit, and you can see its dimensions here is about 4 millimeters by 2 millimeters. And you can see the number of components here is whatever, 10 maybe. And I said, if in a silicon circuit, you've got 100 million per millimeter square. So it's just, there's no comparison in the complexity, you would say. But of course, these are very functional circuits, or very functional elements, so they can achieve a lot. So how do we get a laser onto our silicon? There are 3 different ways. The first way is you build a little micro-optical bench, and you will connect it up via a grating. So a grating, remember, diffracts light. So it diffracts light that's coming at a certain angle, and it diffracts it into the waveguide. So that's used in commercial production of transceivers. Another way of doing it is to make a hole in the silicon and then to transplant the laser, which is also a waveguided device, and couple the light from the laser directly into the silicon. And the third way is by wafer bonding onto the silicon substrate and organizing and arranging so the light in the waveguide couples into a 3-5 part where it gets amplified and then gets sent down the rest of the fiber. So there's various advantages and disadvantages to those techniques. And due to the disadvantages, we're proposing to use transfer print technology to do the integration. So transfer printing technology, you may have heard about it from Hema earlier on in the lecture series, involves the transfer of the laser directly into the silicon. So it can directly reproduce this and this situation. So we can transfer a very thin layer of 3,5 gain material onto the silicon, or we can transfer it into a hole over here and butt couple it to the waveguide. The advantages of that are multifold. One is that a circuit only requires one laser per circuit, for example. So if I look at this circuit here, which is a receiver, so it needs detectors, you can imagine the vast footprint here are associated with these waveguide devices and these phase control elements. The photodiodes are way down here, and only a fraction of the circuit is needed, of the area of the circuit is needed for the photodiodes. So there's only a very sparse usage of the 3,5 material on the silicon circuit. So this transfer print technique makes very efficient use of the 3,5 materials, such as these lasers here. So each one of these long and narrow objects is a laser. So those can be picked and placed onto your circuit and in a very effective manner. And that's the technology that we are developing. So for example, here we've placed 4 different lasers here into a trench into the silicon. And over here you have a coupling waveguide, a ring, a delay line, and a waveguide. So we can couple our laser light directly in, shine it into the waveguide, and at the end get our laser light in our circuit. So we can integrate and power up the silicon circuit via this way here. We can imagine going further with this device, and this is what, for example, is something we're very interested in pursuing. So what we have to do is integrate what are called active gain providing elements like a 3,5 semiconductor and a passive, which is a waveguide circuit. In this case here, this is going to be a tunable laser. So in a tunable laser, you want its wavelength to be single frequency and to vary according to some control parameter. And what we effectively have here is a ring resonator. So there's a ring here, and it's got a certain resonance, and you've got 2 of these resonances, and that creates a Vernier effect. Only when the 2 resonances are simultaneously satisfied will you have a total resonance, and that's then fed back into this gain chip, and from that you can generate a tunable laser. So you can see the elements that are needed in order to perform such an integration. It's the making of this laser here, it's transfer printing, it's coupling, it's the design of the silicon circuit, it's the making it active in some fashion by integrating on some control elements, in this case heaters, and taking that light out of the device. So it's a co-integration. So our goals in the Monolithic and Heterogeneous integration team are to demonstrate advanced functional circuits for communications and biophotonic applications. So what we want to show is that everything can be done within IPIC, that we're really all working together in order to achieve these circuits. So there's a complex arrangement of going really from atoms to systems in terms of the materials design all the way to testing the circuit in the system application. So there's a lot of work needed, and we would like to show that actually we can benefit from each other, and we can generate novel circuits. So for example, this is a circuit here where we would like to generate in this example here, 4 different wavelengths, what's called a comb source, where each of these wavelengths are phase locked to each other. And based upon that, we can do some modulation and send some signals and use low frequency electronics to make a more efficient circuit. So this has all been done by PhD students and researchers. I'll give you an overview of some of them who you may have heard from earlier on in your talks. So as you might have been told, the research environment is that what we want to do is to study and discover new things about our materials and our devices and how we do the integration. But to do that requires a 42-month commitment from the student and from Tyndall. We will support you, and you have to do research. The good news is it's really a very hot topic in science. Everybody is interested in the achievement of this. It's like the start of electronics. So I feel that in a few years' time, we'll have all those design rules and the ability for people to design circuits from their own home, where they don't have to know about the physics of 3-5 semiconductors, and they won't have to know about the technology used to make a waveguide or a circuit. There will be building blocks that they can assemble and put together to build their own circuit for their own application. So of course, we want to communicate our results, and we will attend major conferences. So these are all online at the moment, and they're all free to participate in. But actually, we want to go to the conferences to meet other students and talk to them and learn what they're doing and find out, how the whole thing works. So we have a cohort of students, as I've shown you, all working on different aspects of a common challenge. Therefore, we can have lots of collaboration. We have lots of training, both on the scientific elements, entrepreneurship, and communications. As you know, business is still an important element. We like to research what we're doing, but also we want to help drive it forward. We want to make a more efficient internet. We want to minimize the energy that's been used in these data centers. We want to make functional circuits that are going to benefit society as a whole. And we want to communicate that in our outreach activities. So overall, when you've got your PhD, it would be a springboard for a job in industry or academia. And we see that the demand is everywhere from Cork to anywhere in the world. As you know, in Cork, we have Facebook doing high technology. We have a lot of startup companies who are doing communications. And at the same time, Google and Apple down in Silicon Valley are all looking for people who know about these things. So if I look at my last slide, our vision for 2025, the end of IPIC 2, is that we really will have a significant evolution of photonic integrated circuits, that they have gone from the baby steps of trying to get devices to work to actually being fully working and us being able to design those circuits and build them. We want to see the adoption of integrated photonics. As I mentioned, every mobile phone has a silicon camera chip. So that has to be produced at really, a few cents each. The latest iPad, for example, has a LiDAR chip. And a LiDAR chip has a laser source. It's got a multi-element laser source, quite a sophisticated one at that. And so therefore that is being produced at a very tiny cost. But still, the integration is taking place on the silicon, not on the active device in that situation. So we want to see active device integration. We want to look at the circuits that are going to be enabled by photonics. And of course, we want to generate knowledge through IPIC. So we generate that knowledge, how to do things, generate patents, and really get that knowledge out into industry. And really, we'd love to see a vibrant photonics industry in Ireland underpinned by trained personnel. So that's the end of the talk. And if you have any questions, please don't hesitate to ask.